Hi everyone, in this video we're told the diagram below shows 3 steps that are constructed out of toothpicks, and then it tells us to determine how many toothpicks would be needed to build 50 steps. Now, in the diagram, of course, I could just, I could build the next steps, count the number of toothpicks, and then I could build the step after that and count the number of toothpicks up until I get 50 steps. But as you can probably imagine, that is going to get a little bit onerous. So a better way to do this is to treat this as though it's a sequence, to figure out how many steps are required to build, or how many toothpicks are required to build one step, how many toothpicks are required to build 2 steps, 3 steps, and then try to figure out if we could come up with a formula for n steps. So where t sub n is the number of toothpicks, and n is the number of steps. So the first thing that we can do is let's just do a little bit of counting, and we'll see if we can see a pattern. Let's suppose that we look at a good strategy is to make a table of values anytime that you're looking for a pattern in a particular problem. So let's say that n represents the number of steps, and t sub n represents the number of toothpicks required to build that many steps. So for one step, I would have 4 toothpicks. So 1, 2, 3, 4. Okay? For 2 steps, I would be adding 1, 2, 3, 4, 5, 6 toothpicks. So I would need 10 toothpicks. For 3 steps, I would have, I would have to add 1, 2, 3, 4, 5, 6, 7, 8. I would have to add 8. I would have to add 8 toothpicks. So I would have 18 total toothpicks for 3 steps. And then let's see, let's just draw out the next step. So we would add 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So now I'm adding 10. So for 4 steps, I would need to add 10 more toothpicks. So I would have 28. So, it's kind of hard to see that there's a pattern here, but we can calculate what are called the first differences. We can see if there's a pattern between the finite differences. So to calculate the finite differences, I would do 10 minus 4, which is 6, 18 minus 10, which is 8, 28 minus 18, which is 10. So now it seems like the number of toothpicks required to build each successive step is going up by 2 each time. So if you look at this 6, 8, 10, we've got this constant increase of 2. So presumably for the next step, we would require 12 more toothpicks, which would mean that we would require 40 toothpicks. So now, we could continue this pattern all the way down to 50 toothpicks, but it's probably better here to try to write out a formula for the nth term in this sequence. So one of the things to note is that here we have, these are called the first differences. So these are the first differences. And these are called the second differences. The third differences would be if I would have subtracted, if I would have calculated 2 minus 2, which is 0, 2 minus 2, which is 0. That would have been the third differences, but that's not required here because we can see that the second differences are constant. Now, if you recall, the second differences are constant for quadratic functions. So this implies that we're going to have we're going to have t sub n having a quadratic dependence on n, and we can show that this is true. So if we actually say that, let's suppose that we have n, and then this is going to be t sub n, where t sub n is equal to an squared plus bn plus c, where a, b, and c are all not equal to 0. Well, we can show that this is actually that the second differences of this discrete function are actually going to be constant. So if n were 1, then t sub 1 would be a times 1 squared, which is just a, plus b times 1, which is b, plus c. So t sub 1 would be a plus b plus c. So we would have a plus b plus c. Whoops. T sub 2 would be equal to a times 2 squared plus b times 2 plus c. So t sub 2 would be equal to 4a plus 2b plus c. So this would be 4a plus 2b plus c. The third term, t sub 3, would be equal to, let's see here, 9a. I'll save you guys the arithmetic here. So it's 9a plus 3b plus c. And the fourth term, t sub 4, would be equal to 16a plus 4b plus c. So t sub 3 would be 9a plus 3b plus c. The fourth term would be 16a plus 4b plus c. Okay, so now that we have 4 terms, let's go ahead and we'll calculate the first and the second differences here. So let's just get rid of all these calculations that I've shown here so I can make some room. And we'll put that up here for now. So the first differences, let's see, the first differences we would have 4a minus a, which would be 3a. We would have 2b minus b, which is just b. And we would have c minus c, which is 0. If I did 9a plus 3b plus c minus 4a plus 2b plus c, I would get 5a, because 9a minus 4a is 5a. 3b minus 2b is just b. And I would have c minus c, which is 0. And then I would have 16a minus 9a, which is 7a. 4b minus b is just b. And c minus c is just 0. So you can see what happened when I calculated the finite differences is that these constant terms essentially got eliminated. They were subtracted out, because if I take a constant and I subtract the same value, it's going to be 0. So I'll just be left with these expressions. So notice here that the linear term, in the first differences, I now have the coefficients of the linear term. So I have b, b, and b without. So I've got this constant difference that I'm adding each time, which is the constant difference from the linear term. Now, if I calculate the second differences, notice what'll happen. I'll subtract 5a plus b. From 5a plus b, I'll subtract 3a plus b. So I'll get b minus b, which is 0. 5a minus 3a, which is just 2a. And next I'll have 7a minus 5a, which is 2a. And b minus b, which is 0. So we can extend this now. If we extend this to the next term, we would have had 25a plus 5b plus c, and let's see if that pattern continues. we would have had, for the first differences, we would have had 9a plus b, and calculate the second differences, and then we get 2a. So notice here that the second differences are all for a quadratic, for a quadratic equation, or for an equation that has degree 2, the second differences are equal to 2a. To 2a. And they're constant. So what we can say is that in this pattern that we have above, we know that our explicit formula for the nth term is going to have a quadratic dependence on n, and we know that 2 times this a coefficient is going to be 2. So we have that. Let me write this in a different color. We know for our particular example that our equation will have a quadratic dependence on n. Or we could, another way to say that is just to say that it's quadratic in n. So it will be quadratic in n. Will be quadratic in n. So we have that our formula t sub n is going to be equal to an squared plus bn plus c. So we have that 2a should be equal to 2. So from our second differences, we have that 2a should be equal to 2, and thus a is equal to 1. So we have that t sub n is equal to n squared plus bn plus c. Now the next step is to figure out what b and c are. So we have to figure out what these two coefficients are. And notice that, well, let's see here. So one thing that we could do is we know that t sub 1 is going to be equal to, well, t sub 1 is going to be equal to 4, which is equal to 1 squared plus b plus c, where I just input 1 for n. Now I know that t sub 2, well, if we go back to our table of values, t sub 2 is equal to 10. So that's going to be equivalent to 2 squared plus 2b plus c. Okay, so let's see what happened here. Well, I've got a system of equations. Now I can do, if I subtract t sub 2 minus t sub 1, well, that's going to be equal to 6, which is equal to 4 minus 1, which is 3, plus 2b minus b, which is just b, plus c minus c, which is 0. So I've got this equation here. I've got that 3 plus b is equal to 6. So thus b should be equal to 3. And now that I know this, I can substitute sub b is equal to 3 into the formula for t sub n, into t sub 1, and I have the following, that t sub 1 is equal to 4, which is equal to 1 plus 3 plus c. So thus c is equal to 4 minus 4, which is 0. Okay? So now we can go ahead and so therefore, the formula for the nth term is t sub n is equal to, let's see here, t sub n is going to be equal to n squared plus 3n. So for 50 steps, and remember that t sub n represents the number of toothpicks needed to build n steps. So for 50 steps, we have this. We have that t sub 50 is equal to 50 squared plus 3 times 50. 50 squared is 2,500. And 3 times 50 is 150. So we have that this is equivalent to 2,650. So therefore, for 50 steps, you would need 2,650 toothpicks. So a problem-solving strategy that we just learned in this lesson is that if we have a sequence and we're having trouble coming up with an equation for that sequence, one method is to build a table of values and then look at the finite differences. If the first differences are constant, then the equation is going to have a linear dependence on n. If the second differences are constant, the equation is going to have a quadratic dependence on n. If the second differences are not constant, and the third differences are constant, then we know that the equation is going to have a cubic dependence on n. And then we could use that to help us build an equation. So this is a very useful problem-solving strategy.